Hello students, and a very warm welcome to all of you. Today we're kicking off a really important chapter, Chapter 25, all about the skin. We're going to zero in on pigmented lesions, and we'll follow the entire journey, from a simple mole right up to the very serious melanoma. So, let's begin.
For many, many years, even brilliant pathologists thought the skin was, just a simple barrier, a sort of protective covering. But as we now understand, that view couldn't have been more wrong. The skin is so much more than just a wrapper for our bodies.
I mean, just think about it. It's actually the largest organ in our body, and it's incredibly complex. Yes, it's a physical and an immune barrier, that's true, but it's also a sensory organ, right? It's absolutely crucial for synthesizing vitamin D, for regulating our temperature, and it even hosts this entire ecosystem of microbes. A very, very busy organ indeed.
Right then, let's dive into the main topic. We're going to start our discussion of pigmented spots by getting to know the main character in our story today, the melanocyte cell. Okay, now this is something students often get mixed up about, the difference between a freckle and a lentigo. The difference is fundamentally important, so please pay close attention. A freckle, which we call an epiphysis, is all about increased melanin production when you're in the sun. That's why they tend to fade in the winter, you see. But a lentigo is different. It's about an increased number of melanocytes in the basal layer. The actual cell count is higher, so it doesn't fade. Think of it like this. A freckle is one factory working overtime, while a lentigo is more factories being built. Please remember this distinction. Now, let's build on that idea and move to the common mole, or what we technically call a melanocytic nevus. Now, these are benign neoplasms, basically benign tumors, and practically every single one of us has at least a few. So, a very logical question comes up. We know that many moles actually have cancer-causing mutations, so why on earth don't they all turn into cancer? Well, the answer lies in this absolutely beautiful biological safety mechanism, oncogene-induced senescence. I know, it's a fancy term, but all it means is that a cell with a cancer gene, an oncogene, is smart enough to hit the brakes and enter a permanent state of growth arrest. It stops itself from ever forming a tumor. It's amazing. And this analogy just illustrates the concept brilliantly. Think of a BRAF mutation, which is super common in moles, as a stuck accelerator pedal in a car. The car wants to just go faster and faster, completely out of control. But the cell is very smart. It has an emergency brake, a protein called P16. So it slams on this P16 emergency brake. The mole is the car, and now it stops safely on the side of the road. And over a person's lifetime, a mole doesn't just stay the same. It matures, it evolves. It starts its life as a junctional nevus, with these little nests of cells right at the junction of the epidermis and the dermis. Then it grows into a compound nevus, with nests in both layers. And finally, it can become an intradermal nevus, where the nests have moved entirely into the dermis, and it often loses its dark color. This whole process is a sign of senescence, of it just getting older and less active. Now, what's really cool is that you can see this progression both clinically, just by looking at the skin, and microscopically. So on the left here, you see a junctional nevus. It's flat. It's uniform, very orderly. And on the right, a compound nevus. See how it's more raised, more dome-shaped? The nests have moved deeper. But what do they both have in common? Look closely. They have symmetry and a nice uniform color. These are the classic hallmarks of a benign, completely harmless lesion. But sometimes things start to look a bit, different. And this brings us to the atypical or dysplastic nevus. Now listen, it is not cancer, but it is a very important warning sign that we must pay attention to. Clinically, you can spot the difference pretty easily. Dysplastic nevi are often larger, usually more than 5 millimeters. And just look at the borders. They're not neat and clean anymore. They're irregular. The pigmentation is all patchy and variable. It's starting to lose that orderly, predictable appearance of a common mole.
So what is happening here? Well, genetically, this is often linked to an inherited problem with the CDKN2A gene. And what is that gene code for? Do you remember? Our P16 emergency brake? So the brake itself is faulty. And under the microscope, we can see exactly what that means. Architectural disorder, the nests of cells are messy, they're merging together, and the cells themselves show atypia. They have these irregular, dark nuclei. The order is beginning to break down.
And this, unfortunately, leads us to the most critical part of our lecture, melanoma. This is what happens when that orderly system completely dissolves into chaos.
Just look at this. It's so powerful. Order versus chaos. On the left, you have a benign, symmetrical mole. It's predictable. It's safe. On the right, a melanoma. The borders are all over the place. The color is completely chaotic. You've got shades of brown, black, even red. This is the visual signature of malignancy.
Now, to help us spot this chaos as early as possible, we have a critical clinical tool. And you must know this by heart. It's the ABCDEs. A is for asymmetry. B is for irregular borders. C is for variegated color. D is for diameter, typically anything larger than about 6 millimeters. And, what I think is most important, E is for evolving. A lesion that is changing is a lesion that is screaming at you that something is wrong.
Now, inside the skin, melanoma also has two phases of growth. The first is called radial growth. This is when it spreads horizontally, just within the top layer, the epidermis. And at this stage, it has no potential to metastasize. It can't spread. But then, it can switch to vertical growth. This is when it invades downwards into the dermis, where all the blood vessels and lymphatics are. So the crucial point is this. This is the moment it gains the ability to metastasize and become deadly.
Let's just look under the microscope one more time. Order versus chaos. On the left, you can see those lovely, orderly, well-behaved nests of a benign nevus. The cells are uniform, they're disciplined. And on the right, well, it's total anarchy. You have disorganized, large, atypical cells just invading everywhere. There are no rules anymore.
And this anarchy is driven by very specific genetic hits. First, you get these activating mutations in pro-growth pathways, like BRAF or NRAS. That's our stuck accelerator. Then, you get a failed safety brake, the loss of CDKN2A, our P16. And finally, the cell achieves a kind of immortality by activating TERT, an enzyme that maintains its telomeres so it can just divide forever and ever. So you have the accelerator stuck, the brakes have been cut, and you've got an infinite tank of fuel. A disaster.
So, you've seen the pathology, you've seen the genetics, the clinical signs, the complete chaos. So I ask you, as future doctors, what is the single most powerful tool that you have against this deadly disease?
It's your eyes and your knowledge. It's the ability to see the difference between that order and this chaos. Early detection is everything. Recognizing the warning signs we have discussed today is the single most critical factor in saving lives from melanoma. Never, ever forget that. Thank you.
All right, everyone, welcome back. Today, we're continuing with Chapter 25, Part 2, and we're diving into something you will see literally every single day in your practice: skin growths. As future doctors, believe me, your ability to tell a harmless spot from a dangerous one, well, that's an absolutely crucial skill. So, let's begin.
So, let's start with a feeling I'm sure every single one of us has had. You're just going about your day, you see a new spot on your skin, and you think, what is that? It's that universal moment, right? A mix of curiosity and maybe, a little bit of worry.
Now, the good news, and this is really good news, is that the vast majority of these spots are completely benign, totally harmless. But, and this is the big but, it's your job as a doctor to recognize the few that are sending up a little red flag, the ones that are trying to tell you something important.
Okay, so first up, let's talk about the common and mostly harmless growths. We can think of these as the good guys. These are the things you'll see all the time in your OPD, and most of the time, you can confidently tell your patients, don't worry about this one. All right, so let's start with a group called adnexal tumors. Now, don't let the word neoplasm scare you. It just means a new growth. And adnexal means they come from the skin's little accessories or appendages. Things like your hair follicles and sweat glands. So basically, these are tumors of the skin's support staff. And the main thing to remember is, most of them are benign.
What's really interesting is just how many different kinds there are. You've got cylindromas, which can sometimes grow so much on the scalp they form what's called a turban tumor. Then you have ecranporomas, which pop up on palms and soles, where all the sweat glands are, and of course the super common skin tag, the fibroepithelial polyp. Now here's the key takeaway. While one is harmless, if you see a patient with many of these tumors, it just might, be a clue for some other condition going on inside the body.
And for those of you who love pathology, here's a beautiful description. Under the microscope, a cylindroma is unmistakable. The cells form these little islands that fit together perfectly, just like a jigsaw puzzle. It's a classic sign.
Okay, Cello, let's move on to our next category, the bad guys. Now, I want everyone to pay close attention here. This is especially important for us in India with our kind of intense year-round sun exposure. We're now talking about premalignant lesions. These are the sun's early warning signs.
Now, the most important thing to get in your head about actinic keratosis is that it is not cancer yet. It is, however, a clear step on the road to cancer. Think of it as a direct message from the skin saying, hey, I've had too much sun damage over the years. And just look at this picture. This is an amazing illustration of how dramatic these can get. This thing is called a cutaneous horn, and it's literally what it looks like. It's an extreme pileup of keratin that's growing out from an actinic keratosis underneath.
So what's actually happening at the cellular level? This slide shows it perfectly. On the left, you see nice, normal skin. All the layers are neat and tidy. But on the right, in actinic keratosis, look at the bottom layer, the basal layer. The cells are starting to look weird. They're abnormal. We call this cytologic atypia. The very foundation is starting to crack.
And that abnormality, that is exactly why we have to take these seriously. Because if you leave them alone, a certain number of these actinic keratoses will keep changing, keep getting worse, and eventually become a full-blown invasive cancer, specifically squamous cell carcinoma.
Okay, now we come to the ugly section. This is probably the most critical part of our discussion today. We're talking about actual malignant tumors, and we're going to focus on the two most common types that you are absolutely guaranteed to see in your practice.
So let's compare the two big ones side by side. You have basal cell carcinoma, or BCC. This is the most common cancer in human beings, full stop. But the good news is it's lazy. It's a slow grower and it almost never metastasizes or spreads. Then you have squamous cell carcinoma, or SCC. It's the second most common, and while its risk of spreading is still low, it's definitely higher than for a BCC. Have a look at this image. This is a textbook example of an invasive SCC. Look at the key features. What do you see? It's a raised nodule. You can see it's ulcerated in the middle, it's broken down, and look where it is, on the scalp, a classic sun-exposed area. If you remember only one sentence from this entire lecture, make it this one. The number one cause, the most important reason people get cutaneous SCC is DNA damage. And what causes that damage? UV light from the sun. Simple as that. Now let's focus on basal cell carcinoma for a moment. I want this fact burned into your brains. It is the single most common invasive cancer in human beings, period. Not just here, but worldwide. You will see this, I guarantee it.
Now on this slide, you can see the two main ways of BCC can look. The picture on the left is the absolute classic. It's a pearly, almost shiny-looking little bump, and you can see those tiny, squiggly blood vessels on the surface. But look at the one on the right. That's a pigmented BCC. It has melanin in it, and this one is tricky because it can fool you into thinking it's just a regular mole.
So what's going on at the molecular level? How does this happen? Well, it's all about something called the hedgehog pathway, but forget the complicated name. Just think of it like a faulty light switch. Normally, you have a gene called PTCH. That's the off switch. It keeps cell growth under control. But then, UV light from the sun damages this gene. It breaks the off switch. So now, another protein called SMO is permanently on. The on switch is stuck. And that triggers a chain reaction that leads to uncontrolled cell growth and finally, a tumor. All right, let's move to our final section. Let's pull all of this together and summarize the key things you absolutely have to take away from this lecture. So, to wrap it all up, here are the crucial points. Number 1, sunlight is the main villain of our story. Number 2, you must learn to recognize the warning sign, which is actinic keratosis. 3, know your enemy. BCC is super common but slow, while SCC is less common but more aggressive. And finally, and this is the most important message of all, early detection is everything. If you catch these things early, they are almost all treatable.
So I'll leave you with this final thought. Our skin is our body's wall, its first line of defense against the whole world. Now that you have this knowledge, I want you to ask yourself, how are you going to use it? How will you teach your patients, your family, your community to better protect this amazing, vital organ? Think about it. Thank you.
Hello, everyone, and welcome. So today, we're going to look at the skin in a slightly different way, not just as a simple covering, I want you to think of it more like a battlefield, a proper battlefield where our own immune system is constantly at work. Sometimes it's fighting invaders, which is great, but sometimes, and this is the tragedy, it starts fighting itself. We're going to explore exactly how these battles create the rashes and blisters that you will be seeing in your clinics. Cello, let's dive in. Right, have a look at this. Look closely. This is not just some rash, okay? This is the aftermath of an immunological war. These thick, scaly plaques, this is psoriasis, and they are solid evidence of our own immune cells clashing just beneath the surface. Today, our job is to understand the soldiers and the weapons involved in this internal battle. So, first up, let's talk about the foot soldiers of our immune system. I'm talking about the T cells. Now, in many common rashes, or dermatoses as we call them, these T cells are actually the main culprits. It's like a civil war where our own soldiers start attacking the walls of our own city, in this case, the epidermis. Okay, look here. On the left, you see a classic case of acute eczematous dermatitis. See that redness, the oozing? It looks wet, doesn't it? Now look to the picture on the right. This is what we see under the microscope, and you can see exactly why it's wet. All that white space between the pink skin cells, that's fluid, edema, that is seeped into the epidermis. And this process has a name. This is a key term for your exams, so listen carefully. It's called spongiosis. And the name is perfect. Just think of a sponge soaking up water. The epidermis gets all waterlogged with this fluid, and it literally pushes the keratinocytes apart. This is the fundamental process, the absolute basic pathology in all forms of eczematous dermatitis. So how does this T-cell attack actually happen? Well, it's a classic type 4 hypersensitivity reaction. Some chemical, maybe from a plant or some metal, touches your skin, it acts as a hapten, it binds to your own proteins, and boom, you've got a new target. The Langerhans cells, or scouts, present this new target to the T cells in the lymph node. Then, the next time you're exposed, the memory T cells rush to the site, they release a storm of cytokines, and that is what causes the spongiosis and that horrible, itchy, weeping rush. Okay, now let's switch gears and contrast this with our next big case, psoriasis. Just look at the picture on the left. It's completely different from eczema, no? It's thick, it's raised, and it's covered with a silvery white scale. This dry appearance is a huge clue. And when you look at the histology on the right, you see why. There's no spongiosis here. Instead, you see a massively, massively thickened epidermis. And this thickening also has a name. It's called acanthosis. This is another one of those high-yield terms, so make a note. It's what happens when the keratinocytes just start proliferating too much, way too fast. It's like the immune system is constantly shouting at the skin cells, grow, grow, grow. And that's what causes those raised plaques. You see, psoriasis is fundamentally an autoimmune disease. Your T cells, specifically types like Th1 and Th17, they get confused and start this whole cascade. They release cytokines like TNF and interleukin-17, and these are the signals that drive the acanthosis. And this is clinically very relevant, because our modern biologic drugs for psoriasis, they are designed to target these exact cytokines. So let's just quickly summarize. It's a tale of two reactions. On one side, you have eczema, the spongiotic pattern. It's a reaction to something external, and it looks wet because of all that fluid, the spongiosis. On the other side, you have psoriasis, the psoriasiform pattern. This is an autoimmune reaction coming from within, and it looks dry and thick because of the acanthosis. So you see, two different T-cell battles, two completely different results on the skin. Okay, now we shift gears completely. We're moving from the T cells, the ground soldiers, to the antibodies. Think of them as the Air Force. In blistering diseases, it's not cell-to-cell combat. It's more like friendly fire from above, where our own antibodies start attacking the very structures that hold our skin together. And listen, the absolute key to diagnosing these diseases, the most important thing, is knowing the level of the split. Where is the skin breaking apart? Is the blister superficial, or is it deep? The location of that split tells you everything. It tells you which protein is being targeted, and therefore, what the disease is. So let's compare the two big ones. On the left, this is pemphigus vulgaris. Just look at those flimsy, easily broken blisters and the raw skin underneath. Now on the right, you have bullous pemphigoid. See the difference? These blisters are big, they are tense, they are intact. Why such a dramatic difference? Well, it's all about the location of that split. And this slide illustrates the point perfectly. It's a real aha moment. In pemphigus, on the left, the split happens within the epidermis. This creates a very thin, very weak roof for the blister, which is why it breaks so easily. But in pemphigoid, on the right, the split is subepidermal. It's below the entire epidermis. So the whole epidermis lifts off, forming a thick, strong roof. And that's why those blisters are so tense and they stay intact. Makes sense, right? So this process in pemphigus has another very important name for you, acantholysis. Lysis means to break, right? So here the acantho, the keratinocytes are breaking apart. The desmosomes, those little protein bridges holding the cells together, are destroyed. The cells are no longer stuck to each other. They're just floating freely in the blister fluid. This is the histologic hallmark of pemphigus. Now, how do we confirm all this? We use a special stain called immunofluorescence to actually see where the antibodies are deposited. And look at this, it's beautiful. On the left, in pemphigus, the IgG antibodies light up in a fishnet pattern, exactly between the keratinocytes, right where the desmosomes are. And on the right, in pemphigoid, you see a sharp, clean, linear band of IgG right at the base of the epidermis, exactly where the hemidesmosomes are supposed to be. It's a perfect confirmation. To make this totally unforgettable, I want you to just remember this simple analogy. Think of it like a building wall. The pemphigus antibodies, they attack the spot welds, the desmosomes, that are holding the individual bricks together. So what happens? The wall crumbles from the inside. But pemphigoid antibodies, they go for the big foundation bolts, the hemidesmosomes, that are holding the entire wall down to the ground. So what happens? The whole wall lifts off in one big piece. Simple. Okay, everyone, we've covered a lot of ground today. So now, for the most important part, the high-yield summary. This is what you absolutely must know for your exams. Let's quickly revise these key patterns we've discussed. Just look at this table, it puts it all together. Eczema, T-cell mediated, hallmark is spongiosis. Psoriasis, also T-cell mediated, but autoimmune, hallmark is acanthosis. Pemphigus, now we're with IgG antibodies, hallmark is acantholysis, and the target is desmogleins. And finally, bullous pemphigoid, also IgG, but the target is hemidesmosomes, causing a subepidermal blister. You see the pattern, right? Mechanism, histology, and target, they are all beautifully connected. So the key takeaway, the main point I want you to remember from today, is that dermatology is not a superficial subject. A rash, a plaque, a blister, these are not just skin-deep problems. They are windows. Windows that let us look right into the complex behavior of our own immune system. If you just learn to look properly, you can see the entire battle playing out right there on the skin. So please remember this. A lesion is never just a lesion. It's a story that the body is telling you. A story of T cells and antibodies, of antigens and cytokines, a story of structures being built up or torn down. And the real question for you as a future doctor is a simple one. Can you read it?
Hello, students, and welcome. Today we're taking a tour, you could say, right under the skin to understand some very, very common conditions. You are going to see these every day in your clinical practice, so pay close attention. Cello, let's get started.
Okay, so here's our agenda for this session. We'll start with the stuff on top, pimples and all that. Then we're going to dive deeper, literally, into the fat layer to see what happens there. After that, we'll talk about some unwelcome guests, viruses, bacteria, and fungi that just love to cause trouble for our skin.
Right, first up, the most common complaint of all, especially for young people, acne vulgaris. For them, it might just be a part of growing up, but for us doctors, it's a perfect example of pathophysiology in action.
We've all seen this, right? The red bumps, the pustules. It's a familiar picture. But the real question for us as clinicians is always, what is actually happening underneath all of this? What's the engine driving this inflammation?
The fun to hear is really quite simple. Is the follicle open to the air, or is it closed off? On the left, you've got your open comedone, the blackhead. And please remember, that black color is not dirt. It's just oxidized melanin. Now, on the right, you have the closed comedone, the whitehead. This one is the real troublemaker, kind of like a little pressure cooker that can burst and trigger a big inflammatory response.
So these 4 steps, they tell the whole story of how a simple blocked pore becomes an angry, inflamed pimple. It all starts with a keratin plug. Then puberty hits, androgens go crazy, and the sebaceous glands start pumping out sebum like there's no tomorrow. This oily party is the perfect place for a bacteria, Propionibacterium acnes, to grow. It eats the sebum and turns it into inflammatory fatty acids. And what does that lead to? You guessed it, step 4, inflammation and a potential rupture.
And look at this. Now we get to see it under the microscope. This is an open comedone, and you can clearly see that huge, wide open, the technical term is patulous orifice. See how it's just jam-packed with keratin? That is the plug we were just talking about, seen up close and personal.
Okay, so moving on from teenage troubles, let's look at a different kind of redness we see in older patients. This is rosacea, and believe me, it is much, much more than just a simple blush.
The really key thing to remember about rosacea is that it progresses in stages. It doesn't just appear overnight. It starts with simple flushing. Then that redness becomes permanent, and you can see little blood vessels. After that, pustules and papules can show up, looking a bit like acne. And in the final, most advanced stage, you can even get rhinophyma, that permanent thickening of the skin on the nose.
All right, time to go deeper. We're moving down, past the epidermis, past the dermis, and into the subcutaneous fat to talk about a condition called panniculitis.
So to put it simply, panniculitis is just inflammation of the fat layer under your skin. Now, this inflammation can happen in two main places, either in the connective tissue walls, the septa, that divide up the fat, or inside the fat lobules themselves. And knowing this location is everything when it comes to diagnosis.
And this slide shows you the key differential. It's so important. With erythema nodosum, the inflammation is in the septa, and this is the most important part. There is absolutely no vasculitis. Now look at erythema induratum. Here, the inflammation is in the fat lobule, and there is a primary vasculitis, meaning the blood vessels are inflamed. This is the whole game, because that vasculitis can lead to tissue death and explains why erythema induratum can ulcerate while nodosum doesn't.
Okay, now for a big topic, infections. This is bread and butter for any doctor. We'll start with some very common viruses that just love to make a home for themselves in our epidermis.
Warts, caused by, of course, the human papillomavirus, or HPV. But look, they can look very different depending on the specific type and where they are. On the right, that's your classic common wart, Verica vulgaris, with that rough, kind of pebbly surface. Now, compare that to the one on the left, Verica plana, the flat wart. See how much smoother it is?
Okay, so clinically they look like that. But what happens when we take a biopsy? When we look at it in the lab, what is the one pathognomonic sign, the dead giveaway that we are looking for? What tells us for sure, yes, this is HPV?
And here it is. This is the answer, koilocytosis. Just look closely at these cells. Do you see how the cytoplasm right around the nucleus has gone all clear? It creates these little white halos. This is the classic, textbook cytopathic effect of HPV. You see this? You know it's a wart. Next up, another viral infection, molluscum contagiosum. This one is caused by a pox virus, and the clue here is totally different. This time, you're not looking for a halo. No, you're looking for these huge pink oval-shaped things inside the cytoplasm. These are the famous molluscum bodies, unmistakable once you've seen them.
All right, let's round out our discussion on skin infections by looking at our last two culprits, bacteria and fungi.
Now, pay close attention to this one, Bache, because I promise you, you will see impetigo all the time in your pediatric rotations. It's incredibly common, very contagious, and these days, the usual suspect is almost always Staphylococcus aureus. This is the phrase you need to burn into your memory, honey-colored crust. If a parent comes in and describes a rash that looks like this, your mind should immediately jump to impetigo. This crust is nothing more than dried up serum that has leaked out after the little pustules have broken. And finally, we come to fungal infections. This slide is perfect because it shows you both sides of the story. On the left, you have the clinical picture, what you see on the patient, that expanding red scaly ring. And then on the right, you have the proof. You can actually see the fungal hyphae under the microscope living right where they belong, in that top layer of skin, the stratum corneum. For this, just remember one simple rule. The word tinea is followed by its location. That's it. Tinea capitis, capitis means head. Tinea corporis, corporis means body. Tinea pedis, like pedal, foot. That's athlete's foot. The name tells you exactly where you need to look. So after everything we've seen today, from a blocked pore to deep inflammation in the fat to all these viruses, bacteria, and fungi, what is the one common thread? What is the one single fundamental job of the skin that is being challenged, that is failing in every single one of these diseases? Think about it.